Okie dokie. This is going on page 24 when we are done. Today is the day where I'm going to say change and rate of change a lot, and how the rate of change changes and rate of change and over and over again. So we got to make sure we have our focus caps on so we don't get lost in the words. We're going to start by talking about lines. So we're going to start off by something very, very simple and basic that we already fully understand, I hope. So for any linear function, the average rate of change over any length input value intervals is constant. That's something you've known. You have a constant rate of change, it is linear. We agree with that? This says any length, but we're going to talk a lot about equal length input value intervals over and over again, and wordy stuff over and over again. But the reason this is any is because, as you know, there's an infinite number of points on a line, and if I want to go find the slope or the rate of change, whether I choose these 2 points and do the slope, or these two, I'll get the same answer every time, right? So your input intervals don't really matter. You can pick any 2 points you want. And like I just said, and we've said multiple times already, we often think of this as the slope of the line, okay? But lines are really the only things that you have talked about with the rate of change so far. All right, so let's look at this table here. This says the table above gives selected values for the function f of x. Explain why f of x is not a linear function. Words matter in these questions. If you have a question like this and then your answer is f is linear, that makes no sense. It just told you it's not, and you have to say why it's not. All right, so make sure you're paying attention to those sorts of things. So we are not going to go and actually write out your slope formula a bunch of times. We don't need to do that because the little chart can help us take care of that itself. If I do my change in x, my delta x here, 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4. So that's my change in x. Then for the output, it'll be my change in y. It's really the change in f of x, but it's your change in your outputs. 7 minus 4 is 3. 10 minus 7 is 3. 13 minus 10 is 3. Okay? So I got my deltas taken care of. I do need the slope to be able to actually answer this question, though. So I'm going to take a few intervals. If I go from 1 to 2, so the rate of change on the interval from 1 to 2, I know that the slope is just the change in y over the change in x. I have those two numbers. That makes that 3 over 1, which is 3. That makes sense? See where that's coming from? So I'm not writing it all that stuff out every time. And then I'm going to do the from 2 to 4. The delta y over delta x. That's going to be 3 over 2. Okay. Then I'm going to go from 4 to 8. And my change in y over the change in x, is 3 over 4. So I used 3 different intervals, got 3 different numbers for my slope. So is this a line? No. And we already knew that it wasn't, right? Because it basically told us that. But what we have in green, that's kind of our proof. And then we have to use some words and say something like f is not a linear function because average rates of change of f are not constant. Okay. Does that make sense? Yeah. Yes? All right. Any questions at this point? Okie dokie. All right. Now, if this had been constant, that would have given me equal length input value intervals. then I could just look to see if this was constant. Because one of the things that you did in Algebra 1 was look at first and second differences. And these first differences are constant. However, since the change in x is not constant, it is still not around your neck. Put it around your neck. If these were constant and these were constant, then I wouldn't necessarily have to do all of this. So we like consecutive equal length input value intervals, which is, again, something we're going to write 5 million times. Okay. And I will say, when I graded your quiz, overall, the sentence you had to write about the concavity and the rate of change, very well done by most everybody. And, you know, some people had, it was like almost perfect, but there was little things that were missing, so I made little notes. But overall, it was good instead of just being a disaster. I mean, some were a disaster, but so, and those things will get, it will all get better as we go through this, I promise you. Okay. All right, so this one says, consider the quadratic function g of x equals x squared. We're going to complete the table of values, and then I'll just tell you what else we're doing. But if g of x is x squared, I'm going to take -3 and square it. What do I get? 9. Positive or negative? Positive, right. So -1 squared is 1, and 1, 9, 25. Okay. So we will do our change in x. -1 minus a -3. What's that? 2. 1 minus a -1. 2. 3 minus 1. 2. 5 minus 3. 2. You have to be able to add and subtract positive and negative integers accurately without a calculator, or you're not going to get the right answers on things like this. So then we're going to do our change in y. 1 minus 9, -8. 1 minus 1, 0. 9 minus 1, 8. 25 minus 9, 16. Okay. Everybody good so far? Right, we got our deltas on there. So now we're going to actually write down what the average rates of change are. I will tell you, moving forward, since these are constant right here, we're not going to have to actually find the average rate of change every time. We can just kind of look at what's happening with these differences since this is constant. If these were not all the same number, then we wouldn't be able to take that shortcut moving forward. Okay. All right. So over here, I'm going from -3 to -1. And so my change in y over my change in x is going to be -8 over 2, which gives me -4. Then when I go from -1 to 1, gives me 0 over 2. What's 0 divided by 2? 0. Then from 1 to 3, I can put 8 over 2, which is 4. And then from 3 to 5, 16 over 2, which is 8. Okay. So these average rates of change, what can you tell me about them? How are they changing? By 4. Okay. And are they increasing or decreasing? Increasing. So those are two different things that we're going to have to look at for two different reasons. Now, you could also see over here that they're increasing, right? If we hadn't actually found the actual slopes. And I wouldn't see that they're changing by 4. I would say here, this column is changing by 8, right? But we don't usually care about the actual number, and we don't actually care about the actual slope. So I could still say that they are changing at a constant rate, right? And so that's why I don't always have to go here, but we are. So this is my average rate of change. They are not constant. It's not linear. We're not surprised because we knew it was a quadratic, right? But we're going to add another column over here. And this is going to be the change in the average rate of change. Okay. So this column, average rate of change. Next column is the change in the average rate of change. Okay, and remember, we understand that the average rate of change can change. That's what was happening when we were putting the water in the vases, right? So it's changing, and like, how is it changing? So now I look for these differences. 0 minus a negative 4 is 4. 4 minus 0 is 4. 8 minus 4 is 4. So it is changed. The average rate of change is changing at a constant rate. You with me on that? That happens for every quadratic. It's not always going to be 4, but it'll always be constant. Okay? And had we done this over here, had we not gone that far, we had this. These are consecutive equal length input value intervals. If I had done this difference, this would have given me 8, 8, and 8. I can still see that they are changing at a constant rate because I don't care about the 8 and the 4 really. I mean, there's times where we will, but when we're just analyzing it like this, we don't really care about the actual numbers, just how are they related to each other. Okay, we good with that? Because moving forward, we can kind of skip this part here. It makes everything a little bit easier. All right, so here's what we write. And here's where our wording becomes very important. And I went back and forth on how to word this, because remember, your words don't always have to sound exactly like mine, but you have to say all the important pieces. What I write down is either the most concise way I can think of to write it, or in this case, the way I know you're going to see it written, which to me is not the best way to structure a sentence because it sometimes leads to confusion. So I figure we're going to start now with this type of sentence so that what I'm saying right now will make a little bit more sense. Let's write it down and then I'll tell you what I mean by all that. Okay, so what we're going to say here, so it does say, what do you notice about the average rates of change over consecutive equal length input value intervals? So we noticed that they were changing at a constant rate of 4, really increasing. So we are going to say average rates of change of G, we got to say of who, okay? Average rates of change of G. And then this is where we pause and say over consecutive equal length input value intervals of 2. For some reason, sometimes they want that number. Like that was our how the inputs were changing. So average rates of change, pause, over consecutive equal length input value intervals of 2. Then we continue talking about the average rates of change. The average rates of change of G are changing at a constant rate. Okay, with me on that? And I changed colors there because the blue goes together and the pink goes together. And that's what gets confusing for some people if we don't start writing it like that now. I think it would make more sense if we said average rates of change of G are changing at a constant rate over consecutive equally, like just put it all together like that. But this is the way most of the time it is written. Now you can see it written other ways too, but this is the one that I think sometimes leads to confusion when people are reading it. Okay, what questions you got? Anything at this point? Now I'm going to add a little something on here, because when we have quadratics, there's actually 3 different ways to justify it. One is that your rates of change are changing at a constant rate. The second one has to do with second differences, which I know you did in Algebra 1. We'll get there in a few days. And then the third way has to do with how we talk about this change. And it comes up not as much as the rest, but it does come up. So we're gonna kind of just add it as another part and say therefore, because that tells us something else. Here's what I want you to notice. If this was linear, right? If it was linear, then this column right here would be constant. Does that make sense? Because when your rates of change are constant, that makes it linear. My change in the average rate of change is what is constant. Therefore, the rate of change of the quadratic is a linear function. The quadratic is a quadratic, but its rate of change is linear. Can you follow me on that a little bit? A quadratic is a quadratic, but its rate of change represents a linear function because this is a constant. That pops up every now and then, and if you can at least, that's the only function we talk about where we talk about the rate of change as another function. So that should be helpful, all right? Quadratic is a quadratic. Its rate of change changes at a constant rate. We could also say that its rate of change is linear, just a different way to say it, okay? So we can say, therefore, rate of change of G is linear. It's not saying the function is linear. The rate of change of the function is linear. And that will actually make a whole lot of sense in calculus. That's like a lot of what you do. It ties to a lot of things with that. So not that you do quadratics the whole time, but how they're related. But I'll repeat, so, you know, it's not like we just do this and we never look at it again. We're going to repeat it. We're going to see it in different ways. It's all going to be fine. Sometimes you have to let it marinate in your brain a little bit. It doesn't always just that first day. But are we semi-okay right now? Semi-okay? All right. Flip it over. The back will be better. It's going to be a lot of writing, but I'm not going to talk about a linear rate of change anymore. Okay. So here's one way that you'll be asked these questions. We have some tables, and it says for each one, determine if the function can be linear, quadratic, or neither. Eventually, we'll have some other things added, but that's as far as we're getting right now. So we always start with finding our change in x. So 2 minus 1 is 1, 1, 1. When those are the same, that's good because that's really going to mean less work for us in the end. Then we do our change in y. 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5. Okay. So is this function linear? No, because if it was, those numbers would be the same, and they're not. So then I go on to find the change in that rate of change, and that gives me 2 and 2. And those are the same, right? We don't have a ton of data, but that's okay because we didn't have to do a ton of numbers. But for what the pieces that we have, those are the same. So what would we say this function is? Quadratic. Okay, so here's how we answer this. We say it's quadratic. Okay, got to answer the question first. Then we can go on to say average rates of change of f. Okay, here's something else I need to point out after grading those quizzes. This is a lowercase f. If you put a capital F, you're wrong. That means something completely different. You don't even know what that is yet, but you're not saying what you think you're saying. Because there were quite a few people, the thing you had to write out, the name was H. Some of y'all had some capital H's. And those intervals that went from T1 to T2, some of y'all had some capital T's. That is wrong. I didn't count it wrong. I just kind of wrote over it this time. Next time I will, because it means something completely different. It's a completely different name, a completely different function. So if you have cutesy handwriting and everything you do is capital or everything you do is lowercase, that's great when you're writing whatever. When you're writing this stuff, it has to match or you are saying something else, okay? And notation is a huge part of this course. Like it has got to be dead on accurate. All right, so average rates of change of f, and then I will say over, and I'm going to abbreviate consecutive with consec. That's fine. It's kind of all I can abbreviate right now. Over consecutive equal length input value intervals of 1. Right. So my average rates of change of f, I have to go back and finish what I was trying to say in purple, right? Average rates of change of f are changing. How are they changing? At a what? Constant rate. Good. At a constant rate. So the question last period was, we got to say all that to get credit? Like, to get some credit is what I said. I said, you got to say all that to get any credit. On the actual exam, that's 1 point. It's all or nothing. And right now I'm giving you partial credit because we're learning and we're, you're getting there. But yeah, either you say everything that needs to be said and you get a point, or you don't, and you don't get a point. So that's the way it works. What questions do we have? Everybody okay with that? We good? Okay. All right, so let's look at change in x. It's going to be 1, 3, 5. Okay, so that doesn't mean I can't do anything. That just means I don't have consecutive equal length input value intervals, so I'm going to have to actually find the rate of change for these. But I'm going to go ahead and do my change in y's here. So give me 1, 3, and 5. So when I actually go and find the rate of change, I'm going to put 1 over 1, and that's 1. I'm going to put 3 over 3, and that's 1. I'm going to put 5 over 5, and that's 1. All right? So do we think this is linear or quadratic? Linear. And we can, we don't have to say quite as much with linear, which is kind of nice. We can just say that this is linear, and then average rates of change of who? G, right? Average rates of change of G are constant. Because for a linear, the input value intervals don't matter. We found slopes, they're constant, that's all I really have to say. Okay, so it just kind of simplifies. What questions you got? Anything? We good? All right. Let's do this one then. Change in y. So this is 2, 2, and 2. That's good. Oh, I just put change in y. Dang it, that's not a y. Okay. Oh, yeah. Why is my eraser so big? That should be change in x. Change in x. This is my change in y. 1 minus a negative 1 is what? 2. 2 minus 1 is 1. 2 minus 2 is 0. Okay, is this linear? No. So then we go on to see if maybe it is quadratic. What is 1 minus 2? Negative 1. 0 minus 1, negative 1. Your evidence that you're using still has to be correct. So you still have to be able to add and subtract accurately. So it's not linear. Is this quadratic? Yes. So we're going to say quadratic. And then I want you to go ahead and you can model what you wrote on the first one and write out your sentence. I'll write mine out too, and then we'll talk about it. So average rates of change of H, don't forget to name him, over consecutive equal length input value intervals of 2 are changing at a constant rate. So here's the good news. Even though we have to explain and write a lot, it's not like we have 50 different very specific sentences we have to do. There's not that many, and they start to kind of resemble each other, and you'll learn the things that you have to put in. So it gets better. You just need to not let yourself freak out over it, okay? What questions do we have? Anything? All right. So let's move on to concavity. So we've talked about concavity, and we looked at a graph, decided whether or not it was concave up or down, and then that told us something about the rate of change. This time we don't have a graph. We have data that we're going to be able to find the rate of change, and then that'll tell us something about the concavity. So in order for us to make that relationship and make that connection, what do we need to write down? Fun chart, yes. Fun chart. All right, so if my function is concave up, then the average rate of change over equal input value intervals is what? Concave up is related to increasing. Good. Is increasing. And then it says for small length intervals. That statement, remember I just said we're usually not looking at the whole graph. We're usually looking at something in its neighborhood. So we're kind of talking about, very close to each other. And then concave down, that is related to decreasing. Same relationship, just instead of saying, hey, it's concave up, therefore the average rate of change is increasing, we're going to say, hey, the average rate of change is increasing. That means the function's concave up. That's the difference there. Okay, we okay with that? Questions? All right, so let's make this happen. Selected values of the functions are given. For each one, we're going to determine if it's concave up, down, or neither over its domain that they gave us. We're starting the same way. Change in x. 1.1 minus 1 is 0.1. 1.2 minus 1.1, 0.1. And this is 0.1. So the nice thing is that this is equal length input value intervals, so I don't have to actually find the slope, which means I don't have to divide by a decimal. So I'm going to find the differences here. 1 minus 4 is a negative 3. Negative 1 minus 1 is a negative 2. Negative 2 minus a negative 1 is a negative 1. Now, the 3, negative 2, and negative 1, those are not my slopes, right? For me to find the slope, I'd have to take negative 3 divided by 0.1. But if I'm going to take all three of those numbers and divide by the same number, it's not going to change how they're related. Whether they're changing at a constant rate or they're increasing or decreasing, that stays the same. So we don't actually care about the actual slope. But by looking at this, we can say that would the slopes be increasing or decreasing? Increasing. Okay, so my slopes would be increasing. If the rates of change are increasing, would the function be concave up or down? Up. So we're going to say concave up. Okay, and then we explain. We say average rates of change of who? K. Okay. Then we say over consecutive equal length input value intervals of 0.1. And here's where you have to make sure, like, don't tell me that the average rates of change are changing at a constant rate. I don't care about that here. That has nothing to do with concavity, right? The reason I know it's concave up is because my average rates of change are doing what? Increasing. So the average rates of change of K are increasing. I don't like how these sentences split the information. So it is what it is. We good? Questions? Okay. You could be asked a lot of things from a table of values. All right, let's look at the next one. Delta X. Again, we get 0.1 down the line. My change in Y is going to be 3, 3, 3. So what do you think? Concave up, concave down, or neither? Neither. What kind of function is this? It's linear, right? So linear is not concave up or down. And if you weren't sure about it, well, when it's linear, my rates of change aren't increasing or decreasing. So it can't be either one, right? And so we can say neither. Then we can say average rates of change of M are constant. And yes, it is over equal length input value intervals, but it doesn't matter because they're constant, and that has to do with linear, and so I don't have to say all that stuff. If you do, it's fine. It's not wrong. I just don't say it if I don't need to. Why do I want to write extra stuff? Okay. We good? Any questions at all? All right, y'all work on that last one while I pass out your assignment, then I'll write it up there and we'll talk about it. When we're done. You can talk to your neighbor and check with your neighbor. That's always okay. Unless I say it's not for some reason, but. So what do we think? Concave up or down? Down, good. Concave down. And then I would say average, well, let's just spell it right. Average rates of change of P over consecutive equal length input value intervals of 0.1 are doing what? Decreasing. We good? Okay. Now, we did not do a neither of one of these, but there is one on the assignment. Everybody got stuck on it last period. It's actually one of the easier ones. If you don't have, if your first column is not constant, or you don't have a constant rate of change, and your second column is not constant, then your answer is neither. And it's neither because the average rates of change are not constant or changing at a constant rate. Okay? I just didn't have one on there. Does that make sense to you? We're good? Yeah, you're just going to have to let it vibrate. All right, so go ahead and tape this in. And once somebody gets one taped in, I'll show you something. And then you have time to work. You want to make good use of your time. Can you fold yours? And I'm going to use yours as a little example again.